Swayam Prabha. Digital India. Educated India.
Hello, welcome to lecture 9 of this course. In the last class, we learned how to quantize a propagating electromagnetic wave. In this class today, we are going to learn how to quantize a standing electromagnetic wave. It will be followed by a discussion on quantum states of harmonic oscillator, particularly the so-called coherent states. Let us begin our discussion by writing the Maxwell's equations first. Maxwell equations in the absence of charge and current, and these equations are divergence of E is equal to 0, divergence of B is equal to 0, then we have curl of E is equal to minus del B del T, and curl of B is equal to 1 by C square del E del T. Now because divergence of B is equal to 0, we can write B as curl of A, and you know that A is called the vector potential. It is called vector potential. Moreover, please note that this vector potential is not unique, because I can have another vector potential defined as A dash, which may be different from this vector potential A by some, say, gradient of a scalar quantity, say chi. Then if I take curl on both sides of this equation, so I will have curl of A dash is equal to curl of A plus curl of gradient of this scalar quantity, and you know that this is equal to 0, and curl of A is B. So A vector potential is not unique, and these actually help us to make a choice. We can choose the vector potential such that divergence of A is equal to 0. This is known as, this choice is known as Coulomb's gauge, and this is going to be very useful for our treatment. Also, another thing, that because curl of E is equal to minus del B del T, right, here, so I can also write this expression, curl of E is equal to minus del B del T. So instead of B I can write curl of A, and from here I can write curl of E plus del A del T is equal to 0, and therefore I can write E plus del A del T to be some kind of a scalar quantity, say grade of phi, or say minus grade of phi. Therefore I can express the electric field as minus del A del T gradient of this scalar potential phi. So electric field I can express like this, and the magnetic field B I have curl of A. And now from this equation, divergence of E is equal to 0. If I put this expression there, I will have divergence of A, you will just have minus del T divergence of A. I just have to put this equation here, then you will immediately see that you are going to have delta 2 phi is equal to 0. And because under Coulomb gauge divergence of A is equal to 0, I have delta 2 phi is equal to 0. Okay, now what we can also has another choice. We can choose this phi to be equal to 0 because in the background there is no electrostatic potential. If we can always take it like that. In the background there is no electrostatic potential. This is what this choice means, electrostatic potential. And then what we are going to have is this electric field I have as minus del A del T, and B is equal to curl of A. Okay, this is going to be useful for our treatment, of course, under these choices, that is divergence of A is equal to 0, divergence of A is equal to 0, and this scalar potential electrostatic potential phi to be equal to 0. Under this we can express electric field and magnetic field in this form. So now let us discuss quantization of standing wave. Quantization of standing electromagnetic wave, standing EM wave. Let us do that. Consider a set of two plane mirrors separated by a distance L, and this setup supports a standing wave, and the electric field at the mirrors are 0, so the electric field would have, say, this kind of a structure, and we are considering only one mode of the standing wave, and this standing wave is described by the vector potential, say A. So this is, say, OZ. It is directed along OZ direction, so it would be AZT is equal to, it's linearly polarized along, say, eta direction, and we have this A of t sine kz, and the electric field AEZT is equal to eta E of t sine kz, and the magnetic field is BZT, because B is equal to curl of A, so you can immediately see that it would be K cross eta A of t cos of kz. So this defines the electric the standing wave inside this mirror, two mirrors, and A of t and E of t are real quantities, real field amplitudes, and K is the wave vector along z direction, and the boundary condition imposed by the mirrors leads us to the electric field at 0 and the electric field at the other end of the mirror, that is at L, it has to be 0. And from here you can immediately see that you will get sine KL is equal to 0, and which I can write it as sine into some integer into pi. So from here I have K is an integral multiple of pi by L, so K, the wave vector, becomes discretized because of the boundary conditions. Now we have curl of B is equal to 1 by c square del E del T, and B is equal to curl of A. Now if I utilize this equation here, so curl of A, and that is equal to 1 by c square del E del T. If I open it up, then I will get del of divergence of A minus delta to A is equal to 1 by c square del E del T. Now because we are using Coulomb's gauge, so this divergence of A is equal to 0, and therefore I have, because we are directed along Z, so either only Z component will come into the picture here, delta to A delta Z2, so this one, and here I have 1 by c square del E del T. And also you see that if you, because we have already taken A to be like this, so from here I can immediately write that this would be k square A is equal to 1 by c square del E del T. Alright, or I can just write the time dependence of this electric field would be equal to k square c square A of t, which also I can write it as omega square A of t, where omega is equal to c into k. Now let us define a dimensionless variable. So define a dimensionless variable, say alpha of t is equal to 1 by twice of some normalization factor n omega a minus I e of t. This normalization factor, if you look at carefully, because alpha of t is dimensionless, this normalization factor n should have the dimension of electric field. Now if I take the time derivative of this expression alpha of t, then I have 1 by 2n omega a dot minus I e dot t, and this I can further write as 1 by twice n omega a dot I e dot. So e dot, if I just use this expression here, I can write it as omega square A of t, and which further I can write it as minus I omega 1 by twice n omega a plus I a dot. Now recall that E is equal to, earlier we wrote it as minus del A del T. I can utilize this here, and then I will be able to write it as I omega 1 by twice n omega a I e of t. Okay, so this quantity is nothing but, this whole thing is nothing but alpha of t. So I have alpha dot t is equal to minus I omega alpha of t. So what you see is that the standing wave is fully determined, its dynamics is completely determined, this dimensionless variable alpha of t. I am sure you can see the signature of the treatment that we have done in the last class regarding the propagating waves or the traveling waves. Now the next job is that to find out the energy of the mode. Energy of the mode is, as usual, it is epsilon 0 by 2. So you have this electric field E of RT square plus C square B of R of T square, and this is the volume integral you have to do. So say D3R. So this is what we have to calculate, and let us do that. The integration is evaluated over the quantization volume V is equal to L into L perpendicular square, where L is the length of the cavity and L perpendicular refers to the size of the quantization volume along the transverse direction with respect to the mode axis. Now if we put down the expression for the electric field and the magnetic field in the expression, then we can write H is equal to epsilon 0 by 2. We have E of t square sine square kz plus omega square a square cos square kz, and the volume D3R. And you can easily actually work it out into the same way. You just have to evaluate 0 to L sine square kz dz, and that would turn out to be L by 2. And similarly for the cos square kz, that would be again for cos square kz, it would be the same cos square kz dz. And finally you should be able to get this expression. I am leaving it as a exercise for you, or you can simply do it. It is, you should be able to get this expression, E of t square omega square a square t into the volume, quantization volume. Now you know that alpha we have defined as 1 by twice n omega a minus I e. So using this I can write my final expression as epsilon 0 n square v into mod alpha square. Please verify it. This is what you should be able to get. Okay, now exactly the way we have done earlier for the propagating waves, we can now choose our this n, this constant n, as say s cross omega divided by epsilon 0 v under root. Then I can write my Hamiltonian h as h cross omega mod alpha of t whole square. And please note that alpha of t mod square is equal to alpha of 0 mod square, because you remember alpha of t we can write it as alpha of 0 e to the power minus I omega t. So this is the expression for the Hamiltonian. The only difference that we have, what we had in the earlier class, the constant, we had that factor 2 in the propagating wave, but here we are with this factor 2 is not there. This difference is actually due to the fact that the energy of the standing wave is preferentially located close to the nodes of the cavity mode instead of being uniformly distributed as in the case of plane wave. So we can say that a photon in a standing wave, occupies on average only half of the geometrical volume of the cavity. So this is what is different from the so-called traveling wave or the propagating wave. Now let us define a pair of canonically conjugate variable q and p as follows. This treatment is now going to be the similar as we have done earlier, q plus ip, and then we can write down the Hamiltonian h cross omega mod alpha t square as simply omega by 2 q square plus p square. And in analogy with our discussion with plane wave, we can claim that q and p are canonically conjugate variables. We can have q is equal to h cross by 2 under root alpha plus alpha star, and p is equal to 1 by I h cross by 2 alpha minus alpha star. Okay, and if we do the calculations, in fact you will be able to show that q is equal to epsilon 0 v omega by 2 under root a of t, and p is equal to minus epsilon 0 v by twice omega e of t. Okay, so within normalization factor, a of t and e of t are respectively actually similar to position and momentum of a massive harmonic oscillator. Now let us express a A and E as a function of alpha and alpha star, and if we do that, this is you can easily do it. This is similar the way we have done earlier. So you will get 1 by omega s cross omega epsilon 0 v under root alpha plus alpha star sine kz, and this electric field E of zt would be eta I h cross omega epsilon 0 v under root alpha minus alpha star sine kz. Okay, so that's what we are going to get. Now quantization is straightforward because already we established that q and p are canonically conjugate variables, so they will be replaced by the operators. qp is equal to IH cross and alpha star. So because I have already utilized a and a, the symbol a for propagating waves, now here let me use the symbol b. So alpha is represented by this annihilation operator b, and alpha star would be represented by annihilation operator creation operator b dagger, such that b and b dagger, you can verify it, that would be equal to, this commutation relation would be equal to 1. So for standing wave, I have this operator a of z. I can write it as eta 1 by omega s cross omega epsilon 0 v b plus b dagger sine kz, and for the electric field I have I eta h cross omega epsilon 0 v under root b minus b dagger sine kz. Okay, so now you can compare the electric field expression that we obtained for traveling EM wave in the last class. For traveling EM wave, the electric field operator that we obtained in the last class is like this. It was s cross twice epsilon 0 v. V is the quantization volume, and we had a of t e to the power I k dot r minus a dagger e to the power minus I k dot r. Now while okay, this is for propagating wave or traveling wave, and these are for standing waves. Now while both the traveling wave mode and the standing wave mode behaves like harmonic oscillators when quantized, there is a subtle difference with regard to the photon concept associated with standing wave and the traveling wave. For example, for a single propagating wave or traveling wave, for a single traveling wave, the photon has a traveling wave mode, the photon has a definite momentum. It has a definite momentum, say p is equal to h cross k. If you make a measurement, you will always get the momentum to be like that, and it would have a definite energy E is equal to h cross omega. On the other hand, for a single standing wave, for standing wave in a cavity, for because you know that the standing wave is a superposition of two plane waves with opposite wave vectors, the average momentum of the standing wave, average momentum of a photon in standing wave is equal to 0, and because of that, if a measurement is made, then either one will get h cross k as the momentum, or one will get minus s cross k as the momentum. However, the photon in a single standing wave will have energy. It would have a definite energy, so that would be h cross omega. Okay, this is the fundamental difference between standing wave mode and the propagating wave mode for a single mode I'm talking about. So we have established that standing electromagnetic wave when quantized behave like a harmonic oscillator. Now let us discuss some useful quantum states of harmonic oscillator. This discussion is going to be valid for both quanta of electromagnetic radiation, that is called photons, and also the quanta of mechanical oscillators called phonons. Let us now discuss about various quantum states of harmonic oscillators. Earlier, when we discussed quantum mechanical oscillators, we discussed about the so-called number states, and these number states were represented by kate n, where n refers to the number of quanta in the state, and these quanta were known precisely, and they may be photons or they may be phonons. Now in that context, we talked about ground state of harmonic oscillator, and ground states are also kind of number states. Only thing is that there is no quanta in the state. Now I'm going to talk about one very important class of states, that is called coherent states, and these states are particularly useful for optical radiations, and they are represented by this kate alpha, and we'll see that these coherent states are nothing but displaced ground states. Now the number of quanta in coherent states are generally are infinite, and because of that, these coherent states has a definite phase. On the other hand, in the case of number states, the phase is random. In because you know the number of quanta precisely, so there is a uncertainty in phase, and uncertainty in the number of quanta is 0 in the case of number states, and this is also the reason why generally it is very difficult to generate number states experimentally. Okay, now before I proceed further, let me first talk about this displaced ground state. What I mean by that means I can generate a coherent state by just using this ground state if I apply this displacement operator. Okay, so let me first talk about briefly about this displacement operator. Let me define that first. Let us say we have a wave function psi of x, and it has a structure of this form. Say it looks like this, and this wave function is now displaced by some distance, say delta x, and after displacement it takes this form. So it is displaced by delta x, and this is psi of x, and this displaced form of the wave function is, say, it is psi tilde of x. Now you can see that psi tilde of x is actually the same as this wave function psi of x at distance x minus del x. Now if this displacement delta x is very small, then I can expand it into a Taylor series, and Taylor series expansion of this is going to give me psi of x minus delta x, delta psi of delta x, and you will get all other terms. This can I also write at 1 minus delta x plus the terms and psi of x, or I can write it in an exponential form, that would be e to the power minus delta x psi of x. So you see, this is the so-called displacement operator I am talking about. This is what the displacement operator is. Let me make it more formal, because you know that quantum mechanically the momentum operator is defined as minus I s cross delta of x. Here I am talking about displacement along only one direction, x direction. Generally, if it is three-dimensional this thing, then I will have I s cross this delta. All right, so if I so what I can write, so therefore I can write e to the power minus delta of x as, in terms of this momentum operator, I can write it as exponential p by I s cross, where p is the operator here, delta x. So again, you remember that earlier we defined this operator p in terms of creation and annihilation operator like this: I q0 m omega a dagger minus a. Here I am talking about a mechanical harmonic oscillator, but it is equally valid for photons as well, where users have to put m is equal to 1, and for mechanical harmonic oscillator q0 is the 0-point fluctuation, and it was defined as h cross divided by twice m omega. Okay, so in terms of this new annihilation and creation operator, I can write down this displacement operator d here. This displacement operator, I can represent it by this d cap here. Then I have exponential p by I s cross delta x, who is, if I put this expression from here, then I would be able to write it as exponential. Doing all these things, you can see that you can write it as exponential twice q0 delta x by 2 q0 a dagger minus a. Okay, this is what you will get, and this is only for one particular direction, that is along the x direction we have worked it out. Or you can actually you can just write it as later on I will show that you will be able to write it as exponential real part of alpha, and you will have a dagger minus a. I think I will come to this particular point, what I am saying as real this thing. Later on you will see that delta x is equal to twice real part of alpha into this q0. Okay, that's what I'm you can just take it like this, that delta x by 2 q0 is nothing but the real part of this parameter alpha. Now, as you know that x and p are on equal footing, x and p are on equal footing. Okay, equal footing. So the displacement could occur in the momentum direction or any arbitrary direction in the phase space. So we define the displacement operator. General definition of displacement operator, or the expression would be d alpha is equal to exponential alpha a dagger minus alpha star a. So this is what is the definition of the so-called displacement operator is, where alpha is alpha is an arbitrary complex number. It's an arbitrary complex number. Okay, it's an arbitrary complex number. So you can actually write it, simplify it further, because we know from quantum mechanics that if we have two operators a and b, then e to the power a plus e to the power b, this operator, this relation is there, e to the power a, e to the power b, and then you have e to the power minus half a b, the commutation relation between a b. If the operators satisfy these relations a b, right, and b a b is equal to 0, then this identity, this expression that I have written here, this is valid provided this subject to the fulfillment of these conditions. And you will see that in our case here both a and a dagger, they satisfy this, so you can just take it as an operator, say this is a, this is b, then you can put it there in the expression, then you should be able to show that d alpha is equal to exponential, or just let me write it as e to the power minus half mod alpha square, and you'll have e to the power alpha a dagger, and you'll have e to the power minus alpha star a. This is also another form of the displacement operator you can use. Now going back to the fact that alpha, this coherent state, is nothing but the displaced ground state. So this, when you operate on the ground state, 0 get by the displacement operator, one will get the coherent state. So let us see what we will get by our expression that I just got it here. So if I put it there, let me just quickly show you, e to the power minus half mod alpha square, that's a constant quantity. So let me take now, let me put the operator alpha a dagger, which I can write in an exponential form, alpha a dagger to the power n divided by n factorial, where n is equal to 0 to infinity. You may remember that e to the power x, I can write it as summation x to the power n by n factorial, where n goes from 0 to infinity. The same thing here I am doing here. And then for the another expression, I have m is equal to 0 to infinity. This one I can write it as minus alpha star of a to the power m divided by m factorial, then you operate on 0. Okay, so let us do it. It's very simple. So okay, let me just write here. It implies that this kate alpha is equal to e to the power minus half mod alpha square. And now just look at this expression here. If you break it up, you will see that this summation, the first term for m is equal to, okay, let me just open it up, only this one. If you open it up, you will see for m is equal to 0, you will have this kate 0, okay, and for the another then the second term for m is equal to 1, you will have it as minus alpha star a 0. Okay, now because you know that annihilation operator, when it operate on the ground state, it is going to give you 0, and similarly for all other terms. So ultimately you will be left out with only kate 0 only. So therefore I have this summation is going to give me simply kate 0. So therefore I write it as n is equal to 0 to infinity here, alpha a dagger to the power n divided by n factorial, then kate 0. And okay, now it is then second step, let me do this, minus half mod alpha square. You could have it, write it as n is equal to 0 to infinity alpha to the power n by n factorial, and then you have a dagger to the power n operated on this kate 0. Now again, you know that a dagger n operated over k0. First of all, you know a dagger 0 is equal to simply 1 kth1, and a dagger applied on kth1 is going to give you root 2 kth2, and in this way you again a dagger square on the 0. Therefore you see a dagger 1 is there, so if you just put here, so this is nothing but a dagger 0 would be equal to root 2. So therefore I think you are getting the idea, where I can just extrapolate it to a dagger n 0 would be root over n factorial and ket n, and so from here I can write it as e to the power minus half mod alpha square summation n is equal to 0 to infinity alpha to the power n by n factorial root over n factorial and n ket n, and thus I can write the expression for the coherent state as e to the power minus mod alpha square by 2 n is equal to 0 to infinity alpha to the power n by n root n factorial ket n. So this is actually the one of the most popular form of the coherent state. Please note that this coherent state is normalized, and it is very easy to prove it just by utilizing this relation. Now one can get more insight by evaluating the expectation value of the oscillator position and momentum in the coherent state. For example, the expectation value of the position operator in the coherent state, let us evaluate it. So this is the expectation value, and we know that x operator, we can write it as q0 a plus a dagger, and where q0 is the 0 point fluctuation, and that is h cross divided by twice m omega under root. So if I use this, then I can write it as q0, or the 0 point fluctuation, alpha a plus a dagger alpha, and if you work it out, it's very trivial. First term a dagger a ket alpha is going to give you simply alpha alpha. On the other hand, this a dagger operates on the bra alpha, so you will get it as bra alpha then alpha star. So if you utilize it, you can immediately see that it would be q0 into alpha plus alpha star, and which is nothing but q0 twice of the real part of alpha, because alpha is a complex number. And in fact, this is the reason, you see, earlier I used this definition here. We just defined it, say I promise to come back. Yes, here you see I have taken this delta x as twice real part of q0. Okay, this is the reason, because and here you see that this expectation value of position operator is related to the real part of alpha. Similarly, one can find out the expectation value of the momentum operator, and that would be simply alpha p alpha. Again, you know that this momentum operator is simply I m omega q0 a dagger minus a. So if you utilize it, then you can show that this would be simply twice m omega q0 imaginary part of alpha. This is trivial to solve. Now what about the probability of finding n photons in the coherent state? So let us work it out. Probability of finding n photons in the state alpha. This is of course valid for any n number of quanta in the coherent state alpha. So this is given by, you just have to take the scalar product of this quantity mod square, and because you know that mod alpha is equal to e to the power minus mod alpha square by 2, and you have n is equal to 0 to infinity alpha to the power n by n factorial under root, then this get n. Okay, so immediately you should be able to get this expression. It would be e to the power minus mod alpha square mod alpha to the power 2n and divided by n factorial. Okay, now also note that the mean number of photons in the coherent state, or mean number of quanta in the coherent state, is given by this expression. You just have to take the expectation value of this number operator, and this number operator here is a dagger a, and you can immediately see that this is nothing but mod alpha square. So in terms of this mean number, you can express this probability expression like this: e to the power minus n bar, and it would be n bar to the power n divided by n factorial. So you may recognize that this is nothing but a familiar Poissonian distribution. So clearly the probability distribution of a coherent state is Poissonian, and one can just, to give an example how the distribution look like, let me plot it for any this is the kind of distribution you can expect in a Poissonian distribution. So this is what you are going to have. Okay, another important quantity is the so-called variance. So variance of coherent state, variance delta n square in the coherent state, that is given by delta n squared b. So you just have to take the n bar alpha minus alpha n alpha whole square. So if you work it out, it's very straightforward to work out. So if you work it out, you should be able to get, let me leave it for you to do it. What you will get is that you will get this expression mod alpha square, which is nothing but n bar. So variance is equal to the mean number. So variance is exactly equal to mean number for coherent state, in the coherent state. Okay, so this is an important result. Finally, let us look at some properties of the displacement operator d alpha, which is going to be very useful later on in the course. Properties of d alpha. Let me just list them out. Already you know that displacement operator d alpha, one of the expression is of this type: e to the power alpha a dagger minus alpha star a, and immediately from here you should be able to see that if you take d dagger alpha, then you will get d alpha star a minus alpha a dagger, and which is nothing but d minus alpha. Okay, and so this is actually one important relation to remember. And secondly, you can work it out, say d dagger alpha a d alpha, you will find that this would be simply equal to a plus alpha. Let me prove it. To show it, you just have to use this relation, which you know already from quantum mechanics, hopefully, e to the power a minus a. It's called Becker-Hausdorff formula, I think. So you just have to work it out, just have to utilize this relation there. Okay, let me just write it: a b. Okay, let us find it out. D dagger alpha A d alpha, and d dagger alpha is e to the power alpha star a minus alpha a dagger, a e to the power alpha a dagger minus alpha star a. Okay, now let me take it as a here, capital A, and then apply the formula. Okay, so this is my B, so I have here A plus you have the commutation relation between capital A capital B, so that would be alpha star A minus alpha A dagger. You will have here A, and then okay, so from here you will get A plus if you work it out you will simply get alpha. Then let me just work out the next term also. You will have here half A is your alpha star A minus alpha A dagger. Then commutation relation between AB already we have worked out and found that this is simply alpha, and which is a constant, so obviously this term is going to give you 0, and similarly all higher order terms will go to 0, and you will be left out with A plus alpha. So hence it is very straightforward to prove. Similarly you can prove that d dagger alpha A dagger d alpha would be A dagger plus alpha star. Also please note that d dagger alpha d alpha is equal to identity operator. This also you can prove easily. Let me now quickly show you some usefulness of these relations that we wrote. So for example, you can immediately find out what is d dagger alpha x d alpha, because you know that x is equal to q0 d dagger alpha, here it is A plus A dagger d alpha. q0 is the 0 point fluctuation, so if you work it out you should be able to get immediately. Please show it, it's trivial. It would be x twice q0 and real part of alpha. Similarly you can work out the expression for say x square as well as p square, expectation value of x square, p square, and so on, and very quickly you can work out the expectation value. For example, let me just quickly show you this one. So in the coherent state I just have to utilize the fact that these coherent states are displaced ground state, so I can just write it as say d alpha here, and this would be d dagger alpha, and then in between I have x square here. Now because of these properties I have here x, I can send to its identity operator here, that would be d alpha. Then let me put here d dagger alpha x d alpha 0, this case 0. I think you are getting it. This is the identity operator, okay, from here. And because I know this already, I know this relation, just we know that this is x cap plus twice q0 real part of alpha, and the other one is also x cap twice q0 real part of alpha. So it is very straightforward to work it out. If you work it out you will get simply q0 square plus 4 q0 square real part of alpha square, and therefore immediately if I ask you to find out the standard deviation or for say the variance of the position operator, that would be x square x whole square here. It is in the coherent state, and in fact using this relationship you should be able to show that delta x, this standard deviation, would turn out to be simply q0, which is basically the 0 point fluctuation. And in fact similarly you will be able to show that the corresponding standard deviation in the momentum operator also we can work out, and that would turn out to be m omega for a mechanical harmonic oscillator. This is what you are going to get it. In fact, you can verify that delta x into delta px for coherent state, it would be m omega q0 square, and that is q0 square is h cross divided by twice m omega, so therefore it is simply h cross by 2, and this is the minimum uncertainty product. So for coherent state, the product of this position uncertainty and momentum uncertainty is minimum, and that's the reason why these coherent states are also known as Gaussian states. In fact, you can show that the variance of x in the coherent state is equal to variance of the position operator in the ground state, and this is also you can establish, and this is the reason why coherent state is defined as or said to be nothing but the displaced ground state. Okay, let me stop for today. In this class we have learned how to quantize electromagnetic radiation, and also we learned about coherent states of harmonic oscillator. In the next class we'll continue our discussion on quantum states of harmonic oscillator. We'll discuss squid states. It's a very important class of quantum states, and also we are going to conclude module 1 of this course in the next lecture. Thank you.